Hello and welcome, and I hope that wherever you find yourselves today that you are keeping well and staying safe. Now this video will be about latent heat and change of state. And many people think that latent heat is about ice melting and water boiling. And of course they're totally correct. This is exactly what latent heat is about. And it all started with this guy, Scottish scientist Joseph Black. Now in 1761, Black noticed something very unusual about ice melting. He noticed that if you had ice melting at its melting point and you added more heat to it, that this did not cause a rise in temperature of the ice or the water mixture. It just simply melted more ice. And he noticed something very similar with water boiling. He noticed that if you apply heat, add energy to water which is boiling, it doesn't increase the temperature of the water or the steam, it just increases the amount of steam. In other words, it just creates more steam. And from these observations, he concluded that heat must be applied to ice to melt it or water to boil it. In other words, if you have ice at its melting point, you need to add energy to the ice to get it to melt. This heat, this energy added, will cause a change of state, but not a change of temperature. And that's exactly how we define latent heat. We say latent heat is the heat needed to cause a change of state, but not a change of temperature. And that is the definition of latent heat. Now, after watching this video, I hope you will be able to do the following. Define latent heat. Define the specific latent heat of fusion of ice, know the units that it's measured in, and the formula used to calculate it. Similarly, for specific latent heat of vaporization of water, you need to know the definition, the units, and the formula needed to calculate it. You should also be able to interpret what are known as heating graphs, sometimes called cooling graphs. You should know that power is energy divided by time, and know that the unit of power is the watt, which is a joule per second. And you should also be able to do 5 questions in the worksheet that follows here. Some of these questions three of them are quite okay. One is a little challenging, and the last one is actually quite challenging. So that should be good for you. Now, as we have seen, the common definition of latent heat is the heat or energy needed to cause a change of state without a change of temperature. I think we're all familiar with the 3 commonly that use states of matter: solid, liquid, and gas. And the energy needed to go from one to the other without a change of temperature is known as latent heat. To give you an example, if we have water in its solid form, ice, at 0 degrees Celsius, and we have 1 kilogram of that, and we want to convert it into 1 kilogram of water at the same temperature, then the energy we add in order to change its state, but without changing its temperature, is known as latent heat. There is, of course, 2 different types of latent heat. The energy needed to go from solid, to change the state from solid to liquid, is known as latent heat of fusion. Fusion is an old word for melting. It isn't to be confused with nuclear fusion, which is the same word but a very different meaning. So the energy needed to change the state of a solid to a liquid without change of temperature is known as latent heat of fusion. Similarly, the energy needed to change the state of a liquid into a gas, for example, liquid water to water vapor, that energy needed to cause that change of state without a change of temperature is known as latent heat of vaporization. Vaporization being the process of converting a liquid into a gas. Now there's 2 very important definitions coming up here, and you need to pay great attention and learn these. The first is known as the definition of specific latent heat of fusion of ice. Fusion, of course, meaning melting. And the definition of the specific latent heat of fusion of ice is normally given like this. This is the energy needed to change the state of 1 kilogram of ice from solid to liquid without causing a change of temperature. For example, if you have 1 kilogram of ice in its solid form, that's water in its solid form, and it's at 0 degrees Celsius, and you want to convert it into 1 kilogram of water, liquid, also at 0 degrees Celsius, you have to add this much energy. You have to add 330,000 joules of energy. So the addition of 330,000 joules of energy to 1 kilogram of ice at its melting point will convert it all into 1 kilogram of water, still at 0 degrees. So this number is the energy needed to change the state of 1 kilogram of water, of ice, into water without changing the temperature. So this is known as the specific latent heat of fusion of ice. That number is normally written in scientific notation, 3.3 by 10 to the power 5, and it's that number of joules per kilogram, so joules per kilogram. So the specific latent heat of fusion of ice is the amount of energy needed to change the state of 1 kilogram of ice from solid to liquid without causing a change of temperature. This is the exact number of joules per kilogram needed to do that. And of course, if you're trying to melt more than 1 kilogram of ice, you simply multiply by this number by the number of kilograms you have. So as I just said, this number is the specific latent heat of fusion of ice. It's the number of joules, the amount of energy needed to change the state of 1 kilogram of ice without changing its temperature. And obviously, if we have more than 1 kilogram, we simply multiply this number by the number of kilograms we have, which leads to this easy enough formula. The total energy, the total latent heat needed to change the state of a certain mass of ice is the product of two things. First of all, the mass of the ice involved in kilograms multiplied by the specific latent heat of fusion of ice, the constant up there. This formula is on page 58 of your maths tables. Most people don't need that, though most people actually can remember it. And just a very, very quick example, a quick and easy example of using this formula. Well, how much energy is needed to convert 8.2 kilograms of ice, which is at 0 degrees, into water at the same temperature, no change of temperature? The specific latent heat of fusion of ice is 3.3 by 10 to the power 5 joules per kilogram. So we write down our formula from page 58. The mass of the ice is 8.2 kilograms. The specific latent heat of fusion of ice is given in the question. Just multiply them and you get 2,706,000 joules of energy. A quick couple of points. First of all, mass as usual will always be in kilograms. I've often said it in the past. If you convert mass to kilograms, you are never wrong. And secondly, just observe the units of the specific latent heat of vaporization of water. It's joules per kilogram. There is no per degree there. There's no per Kelvin because, as we said several times, there is a change of state but no change of temperature. And before we look at other examples, just to remind you about what is actually on page 58 of your maths tables, we have two formulas in particular. This is the formula for latent heat, the energy needed to change state. And this is the formula for energy needed to change the temperature of something without a change of state. So we use this formula here to calculate the energy gained or lost when there is no change of state, mass by specific capacity by change of temperature. We use this formula, mass by latent heat, specific latent heat, to calculate the energy gained or lost when something does change temperature. It's very important to know both of those formulas. Now, example 2 here is a little bit more challenging and it will use both of the formulas that we have just talked about. Example 2, calculate the total amount of energy needed to convert 500 grams of ice at 0 degrees Celsius into water at 25 degrees Celsius. We're given both the specific latent heat of fusion of ice and the specific heat capacity of water in their appropriate units. Now, when I'm doing a question like this, I actually have to visualize it. It does help me quite a lot to visualize it. So we started off with 0.5 kilograms of ice, 500 grams, it's at 0 degrees. First, we've got to convert that ice from ice at 0 into water at 0, and that involves a change of state. So we will use the change of state formula. And then when we've got our 0.5 kilograms of ice at 0, we have to convert it into water at 25 degrees Celsius. And that, of course, doesn't involve a change of state. So it involves this particular formula. Once we have kind of got it either visualized in writing or in our heads, we simply work out this much energy, that's the energy needed to cause the change of state, this much energy, the energy needed to heat the water from 0 up to 25, and simply add the two parts together. So let's work down through this question. Well, what I did was very simple as that. Always obviously start off with your formula, so I've written my formulas there. The energy needed to cause the change of state is the mass of the ice multiplied by its specific latent heat of fusion of ice. That is 165,000 joules. Then the energy needed to rise the temperature of the now water, 0.5 kilograms of water, up to 25, using that formula is mass by specific capacity by change of temperature. That adds another 52,250 joules. Adding both those together, we get this answer here, 217,250 joules. That much energy is needed to do both of these things added together. Now moving on to example 3, and example 3 adds just another little layer in because it mentions what's known as power. Now a quick revision of power. Power is defined as the energy converted from one type into another divided by the time taken. That formula is in the maths tables, not exactly in that form. I think it uses work done instead of energy converted, but they're exactly the same things. So power is energy converted divided by time, energy in joules, time in seconds, so power is in joules per second. We define that as a watt. Since power was mentioned, I wrote down the formula for power, and we're talking about melting ice for 2 kilograms of ice at 0 degrees into water at the same temperature. So we're talking about a change of state there without a change of temperature, so we use that formula. So how long will it take for an electric heater, which is power of 500 watts, to do this? Well, the first thing I want to work out there is how much energy is actually needed to change the state of 2 kilograms of ice. And I write down the formula. We've got 2 kilograms of ice. There it is. That's the specific latent heat of fusion of ice. Multiply those two together. That's the total amount of energy needed to melt the ice. Now, how quickly is the ice receiving that energy? At what rate is the ice receiving that energy? Well, we're told the power is 500 watts. That means the ice is receiving this energy at the rate of 500 joules per second. So I put in 500 joules per second there as the power. The total energy needed is there, divided by the time. Simply cross multiply and I get time equals that divided by that, and it works out at 1,320 seconds. So the energy, if you add energy at 500 joules per second, 500 watts, to that much ice, it will melt it all in 1,320 seconds. You can convert that to minutes if you want, but it's quite appropriate, quite legitimate to leave it as seconds. Well, now that we've looked at the change of state from ice to liquid and talked about and defined the specific latent heat of fusion of ice, we're now going to look at the transition from the other change of state, which is the transition from liquid to gas, in terms of water, from water liquid to water vapor, which is a gas. Now, the specific latent heat of vaporization of water is defined as the energy or the heat needed to change the state of 1 kilogram of water from liquid to gas without causing a change of temperature. So here we've got water at its boiling point, 100 degrees Celsius. We want to convert it into water vapor or gas, also at 100 degrees Celsius. So we're not changing the temperature, but we sure are changing its state. And we have to add energy in order to change its state. And the amount of energy you need per kilogram of water to turn it from liquid to water vapor, liquid to gas, is a whopping 2,300,000 joules. You notice this is a much larger number than the specific latent heat of fusion of ice. It's about 9 times bigger. So the latent heat needed to go from 1 kilogram of liquid water at 100 to 1 kilogram of water vapor gas at 100 is this. So this is known as the specific latent heat of vaporization of water, and its definition is the heat needed to change the state of 1 kilogram without causing it from liquid to gas without causing a change of temperature. Just let's compare these two numbers for a second. We've already said the specific latent heat of fusion of ice is that number, and the specific latent heat of vaporization of water is this number. This number is property units joules per kilogram. This number is about 9 times bigger, which is telling us that if you want to boil water, you need about 9 times as much energy as if you wanted to melt ice. Now, naturally, if you have more than 1 kilogram of water and you want to change its state from liquid to gas, you This is the amount of energy needed per kilogram. You simply multiply this number by the number of kilograms. That gives us an equivalent formula as for fusion. The latent heat of vaporization, the energy needed to cause a change of state from liquid to gas, is the mass multiplied by the specific latent heat of vaporization of the water. That is the exact same formula as on the top of page 58, but it's one that I think you probably should learn, and if you're ever asked, obviously label it as well. And now we're going to continue on with another couple of examples. They're easy enough once you get your head around them. Example 4. How much energy will it take to convert 300 grams of water at 25 degrees into steam at 100 degrees? Well, I've visualized it here. 300 grams of water, 0.3 kilograms, into water at 100. First of all, this energy change here does not require a change of state, so we use this formula. And then when we've got the water at 100 degrees, to change its state into steam still at 100 degrees, that does involve a change of state, so we use this formula. Applying those formulas, obviously write down the formulas first, as I have. Applying those formulas, we get this. So the mass of the water is 0.3, the specific capacity of water is given as 4180, and the change of temperature here from 25 to 100 is obviously 75. That works out as that. Here comes the change of state. The change of state is the mass by the constant, specific latent heat of vaporization, which we were given there, and that works out as that. You notice it takes a lot more energy to change the state of the water from water to steam than it does to bring it from 25 to 100 degrees. Adding those two together and you get just over 250,000 joules of energy. That's your answer there. You notice I always like to draw a red line under my answer because it highlights it and makes it stand out a little bit. And I've actually just attached on another little part of this to bring power into this question. How long will it take a 3 kilowatt electric kettle to do this? How long will it take a 3 kilowatt electric kettle to add that much energy to the water to cause the rise in temperature and the change of state? Well, power is energy divided by time. 3 kilowatt electric kettle, well, that's 3000 watts, 3000 joules per second, so that's the power. The energy there is what we've just calculated from above, and time, when you work it out, the time is 261.35 seconds. And the last thing I want to look at today is what is known as a heating graph of water, sometimes called a cooling curve if you go the other way. It's just a very, very simple graph. On our y-axis we've got temperature in degrees Celsius, and on our x-axis we've got energy supplied. You notice I haven't put any numbers here. All we need to know is as we go towards the right, more and more energy is supplied to our substance, and it's supplied at a constant rate. So let's just start down here. Well, here we start off with the water at minus 20 degrees Celsius. Obviously, in this particular temperature, water is normally a solid. We add energy at a constant rate and the temperature of the ice increases right up to 0 degrees Celsius. We keep adding energy at a constant rate, but there's no change of temperature for a while. Obviously, what was going on there is the ice is melting. When the ice and the energy needed to do that, of course, is called latent heat of fusion. When all the ice is melted, we are now at water stage. The state is water. And you keep adding energy, we keep adding energy at a constant rate, and the temperature of the now liquid water rises. It rises in a straight line right up to 100 degrees Celsius. At this stage, the temperature stops rising and a change of state occurs. Energy added from now on is known as latent heat of vaporization, and it goes into the process of turning the liquid into a gas without changing its temperature. You notice this stage in the graph is much longer. It takes much more energy to go from liquid to gas than it does from solid to liquid. That reflects the reality that the specific latent heat of vaporization of water is about 9 times the specific latent heat of fusion of ice. As we said earlier, it takes a lot more energy to boil water than melt ice. Now, looking at this graph, a more labeled version of it here, then we can see that I've labeled this transition from solid to liquid here. The ice is melting, which we know as fusion. And this amount of energy here, and if we had units on our graph, we could work it out. This amount of energy here is known as latent heat of fusion. This transition here is known as a vaporization. The water is turning from its liquid stage into its gas stage. And the amount of energy here is known as latent heat of vaporization. If, of course, we had units on our graph, we could work out how much latent heat of vaporization there actually is necessary to cause the change of state. That graph is easy enough to interpret, and there's going to be one very interesting Leaving Cert question based on this very shortly. Now, what happens next is you leave me, you leave the video, you go and do the 5-question worksheet that I've just posted up on Teams. I will continue on here going through the worksheet and showing you my answers. And when you have finished the worksheet, you can either check with the answers on the document I put up in Teams, or you can come back to the video and see how I've worked through these questions. So you go, you do that, and I'll keep going here. Now looking at the answers to this worksheet. The first 3 questions should be manageable enough. 1. Calculate the energy needed to convert 4 kilograms of water into 20 at 20 degrees Celsius into steam at 100 degrees Celsius. Well, there's 2 parts there. 4 kilograms of water at 20, you must convert that up to 100, and that's no change of state, so we use that formula. And then the 4 kilograms from water at 100 degrees Celsius into steam at 100 degrees Celsius does involve a change of state, so we use that version, that formula there. Putting things in, and we're given the constants, and it works out at a whopping 10.5 million joules of energy. You notice a lot more energy needed to change the state than rise the temperature. The second question involves power, and it says an electric kettle is used to convert 350 grams of crushed ice at 0 degrees Celsius into steam at 100. If the kettle has a power rating of 2 kilowatts, 2000 joules per second, calculate the total energy needed and the time taken to do this. Now we have something interesting here. We have 2 changes of state and 1 change of temperature. We have to go from 350 grams of ice at 0 into 350 grams of water at 0, and that means a change of state. The water at 0 then has to go from water at 0 to water at 100, and that doesn't involve a change of state, just a rise in temperature of water from 0 to 100 degrees Celsius, and then turning it into steam involves another change of state, so we use that formula there. It should be easy enough to see what needs to be put into the formulas. The mass is 0.35. Always convert to kilograms. You are never wrong if you do that. I know in some of the experiments it's easier to leave it as grams, but you're never actually wrong if you do that, convert to kilograms. So we work out the 3 different chunks of energy there and add them together, and we get that number of joules. Then the power. Well, power is energy divided by time. So we've got, the power was added at 2 kilowatts, 2000 joules per second. The total amount of energy is there. So the time works out at just over 533 seconds. This question is a little bit more challenging. In making espresso coffee, steam at 100 degrees Celsius is forced into cold milk in a cardboard cup. Assuming that the cardboard cup does not absorb any heat, that means the cardboard cup has a low heat capacity, and that the specific heat capacity of milk is the same as water, 4,180 joules per kilogram per degree, and of course that's given to you, you don't have to memorize this. Calculate the total amount of energy needed to rise the temperature of that much milk from there to there. Well, that's obviously not a change of state, so the energy needed, and the mass of steam to do this. Well, the energy needed to rise the temperature of that much milk from there to there is no change of state, so we use this formula, the mass of the milk, the specific capacity of milk, same as water. I wonder, is that true? And rise in temperature of the milk, 20 to 80, 60. So we want to rise the temperature of the milk by 37,620 joules. Now, This energy is supplied to the milk by steam. So let's just look at that part of the question. Well, the steam. We want, that is the energy needed. So that's the energy. The mass of the steam that condenses, is there, and the specific latent heat of vaporization of steam is there. So that works out at that many kilograms of steam. I've just noticed something interesting about that question, so you could maybe add another term on there, but we'll leave it that way for a second. Now, the last two questions are much more interesting. This question is, and I appreciate the scanning didn't work too well here. This question came up in the Leaving Cert in 2012. It was a half question. The graph shows the variation in the temperature, theta, of 150 grams of crushed ice when it was supplied with energy at a constant rate. So it started with the ice just below minus 3 degrees Celsius. Energy was added to the ice till it came up to 0 degrees Celsius. More energy was added to the ice and its temperature did not change. That means it was melting. Fusion was occurring. This is latent heat there. And then the more energy was added to the ice and its temperature went up. At this stage, of course, the ice, here it was solid. At this stage, of course, it was liquid. And this is where it was transitioning from solid to liquid. That is called fusion melting, and the energy needed is latent heat of fusion. So let's look at the actual questions there. Well, the first question, explain the shape of the graph. Explain the shape of the graph. I'm seeing three parts of the graph here. Part 1, Part 2, and Part 3. And I think I've explained what's happening in each stage there. Well, in Part 1 of the graph, the temperature of the ice increases from minus 3 to its melting point, 0. In Part 2 of the graph is about latent heat. The temperature of the ice remains at 0. There's no change of temperature while a change of state is occurring. And for the third part of the graph here, we've obviously converted all the ice into liquid water. So what did I say about Part 3 there? At Part 3, now the ice is now water and its temperature increases. So I've explained the three parts of the graph there. Maybe in a bit too much detail, but nothing wrong with that. Describe how the energy could have been supplied at a constant rate. Any answer here is kind of acceptable. Electrical hot plate, a heating coil, a water bath, they will all supply energy to the ice at a constant rate. Just notice it didn't mention crushed ice, even though it didn't refer to it in the question. Crushed ice has a larger surface area, so it generally melts faster. The last part, use the graph, estimate the specific latent heat of fusion of ice. The first thing I did there, I'm sure, was write out a formula. Oh, sorry, I did the question up here. So I just looked at the graph here and I said, well, that there is 10 kilojoules. This is the latent heat part of the graph. Here is 59, you can just see it there, kilojoules. So the energy needed to change the state of the water was 59 minus 10 kilojoules, 49 kilojoules, 49,000 joules. Now, the 49,000 joules melted or changed the state of 0.15 kilograms of ice. We were told it was 150 grams. So I wrote down the formula for latent heat of fusion. I put in the energy there that I calculated from the graph is 49,000 kilojoules, 49,000 joules, apologies. The mass is 0.15. So working out, solving for this here, I got a constant of 3266, ooh, a lot of sixes, 326,666.6 joules per kilogram. Little bit lower than the standard answer, but that is what we got from there. Now this fifth question, which curiously I've labeled number 4, from the honours paper of 2014, I found actually quite challenging. Not the physics of it quite challenging, but the actual arithmetic, the numbers turned out to be quite big. So we'll just have a quick look at this question. Define specific latent heat. Definition, easy enough. A drinking glass contains 500 grams of water at a temperature of 24 degrees Celsius. 3 cubes of ice of sides, each of side 2.5 centimeters, are removed from a freezer and placed in the water. The temperature of the ice when added is minus 20 degrees Celsius. Calculate the mass of the ice. And we notice we're given the density of the ice in grams per cubic centimeter, and density is mass divided by volume. And calculate the minimum temperature of the water when the ice has melted. Calculate the temperature of the water when the ice has melted. We're given the specific heat capacity of water, the specific capacity of ice, the specific latent heat of fusion of ice. We're given a lot of constants there, so there's a bit of working out to do perhaps. Okay, let's look. Let's look at each part in turn. Define specific latent heat. It's the energy needed to cause a change of state of 1 kilogram of a substance without a change of temperature. If you actually define specific latent heat of fusion of ice there, that would be grand 2. The energy needed to cause a change of state in 1 kilogram of ice from solid to liquid without a change of temperature. Calculate the mass of the ice. Well, I base this on the formula density is mass divided by volume. So we were told the volume of, or the dimensions of the cube of ice were 2.5 centimeters. So I got the volume by saying length by breadth by height, 2.5 cubed is that. There were 3 cubes of ice. So the total volume of the ice is 46.875 centimeters cubed. We're also given the density of the ice in the question. So I put in density is mass divided by volume. Put in for density, mass is mass, whatever we're looking for, and there's the volume. What I've got there, I just used maths cross-multiplied to work out the mass of the ice as 43.125 grams. Underlined it because that is an answer. Now, here's where it got a little bit interesting. Or complicated, if you want to say that. I said, let T be the final temperature of the mixture when the ice has melted. So T will be somewhere between minus 20 and 25 degrees Celsius, because I think that's what the water was. The ice will gain energy and the water will lose energy. Now, the ice will gain quite a lot of energy, and it will gain energy in 3 different chunks. The ice starts off at minus 20. So the first chunk of energy gained by the ice will be going from ice at minus 20 to ice at 0. That doesn't involve a change of state. So it's mass by specific capacity by change of temperature of the ice. We've got the mass. And you notice I'm leaving everything as grams here. Why is that justified? Well, there's 4 parts to my formula, and every part's got mass, so I can leave it at grams. It makes it a little bit easier. But if you convert to kilograms, that's grand too. So the mass of the ice, the specific capacity of the ice to change the temperature of the ice from 20 up to 0. That's the energy gained by the ice going from there to there. Next thing is the ice melts, latent heat. It melts from ice at 0 to water at 0. So we use that version of the formula there. But it doesn't actually just stay there. The ice then gains more energy from 0 up to the final temperature, which we said was T. So the next chunk of energy is the energy gained by the ice, now water, after melting, going from 0 degrees Celsius up to the final temperature, which we said is T. So that is no change of state involved. Mass of the ice by the specific capacity of water, because it's now water. We were told to take it at 4,200 joules per kilogram per degree, by the change of temperature. And the change of temperature is the difference between T and 0, or 0 up to T. So we call that T, X if you want. All this will be equal to the energy lost by the water. Now, the energy lost by the water will be going from 24 degrees Celsius. I think it said the water started off at 24 degrees Celsius. Did it? It did indeed. Down to T degrees Celsius. So the energy lost by the water will be the mass of the water by the specific capacity of water by the drop in temperature of the water from 24 down to the final temperature, which we've said we'll call T. Call it X if you want. Putting all that together, I got that. And by the way, once you've got this far, the physics is over and you've got most of the marks. It took a lot of working out because the numbers were kind of awkward and you had a lot of calculator work, but I finally got an answer of T equals 15.06 degrees Celsius, which sounds reasonable enough. It's above 0, it's below 24. I just note to myself, this involved quite awkward working out, and most of the marks were given for the formula in this year's question anyway. Okay, there are the 5 questions. Hopefully this was some use to you. Bye. Take care.